Anything else before we get into some new stuff? Or actually, we're going to finish up chapter 8 first. Okay, all right. This test was the first test I didn't have to curve at all, which is great. Right, so a lot of people did pretty well or well enough on the test. If you didn't, even if you did, you can make corrections, get some points back. Don't forget. Okay. So what I try to do is when I'm teaching something new, I try to show you how it's the same idea we've used before, just applied to some new function. So for example, whenever we learn a new function, one of the first things we do is we see what it looks like if I graph it. We want to know the basic look of it, right? So I've got parabolas, and now I've got sine waves, right? I've got all this stuff. I want to know what it looks like, because then I can do stuff with it. I can use the graph to tell when things are going to happen, so forth, right? If anybody surfs, and you look at the surf report, doesn't it go like this, the tide? Of course it does, right? Because the moon goes around, and they go up, and it goes down. Beautiful sine wave. Okay, anyway, that's just one example of a sine wave in real life. Even if you don't surf, it still happens. So another thing we do, besides just graphing functions, is we need to know the inverse of the function. Why do we need to know the inverse of a function? Why? See again? To prove it. Yeah, we need to prove what their inverse is, or we need to develop what the inverse is. But can somebody imagine what is the most, when I say algebra to somebody, could be you, could be somebody else, what do you think the first thing is that comes to mind? What's like the basic, when I say algebra, what comes to mind? Anything? Quadratic formula, sure. What does that do? Doesn't that solve equations? Isn't algebra like solving equations? When you say, if somebody had to sum it up, you could say word problems, just like you're graphing, but really it's about solving equations, right? Okay, so for example, if I had the cube root of x equals 2, how would I solve that? Cube, why? Why do we use a cube? It's the inverse of cube root. And what's the inverse do? It kills the other dude, right? So I can get x by itself. X is currently stuck in a root. I want to free that up. Okay, so we all know this. Just understand fundamentally, if I didn't know powers, but I knew roots, which would be very strange, I wouldn't be able to solve that equation. If I don't know the inverse, I wouldn't be able to solve it. Why you put a 2 there, John? So, if I have sine of x, the question is, what is this? And do you guys remember when we had exponentials? And when we did the inverse, the very first thing we did was graph the inverse, right? And then we actually developed a function. We didn't do something to solve for it. We have to create it. I want you to understand. When you guys learned roots, unfortunately, we just sort of told you, here they are. We should have kind of said, we need the opposite of exponents. We need to figure out what this is. We need to give it a symbol, right? This is what we do. So, this is going to be what we're investigating. So, like I just said, let's graph this first and then talk about the problems with it, right? So can you guys, just on your notes, can you just really quickly sketch out sine x for me? Now let's go like this. Let's go from negative pi up to pi. Let's see if you guys can do that. Just go from negative pi up to pi. Sketch out what sine looks like. Don't reach for that graphing calculator. So if I were you, I would start sort of in the middle and kind of go out from there. What is sine of 0? Sine of 0 is 0, right? So sine starts at 0. Cosine starts at 1, right? Because cosine loves x, sine does not like x. So it's 0 on the x-axis, 0 at 0 degrees. What's it do at pi over 2 when it gets to 90 degrees? What's sine? 1. What about negative 90? What if I went backwards and went down here? I'm about 0 and I go back 90. What is it now? Negative 1. It's on the y-axis, but it's on the negative direction. So it's going to be negative 1 here. And then, of course, at pi and negative pi, when it gets to 180, right? Pi is 180, and negative pi is 180. They both end up in the same place. What is sine here? 0, because again, sine likes y, doesn't like x. This is all x. So here's what the sine graph looks like, at least partially. Can somebody point out the major issue about trying to find an inverse of this? What do you remember about inverses? When does an inverse exist? What must be true? What test must the function pass? Horizontal line test. Does this pass the horizontal line test? Shit! Have we ever found the inverse of a function that didn't pass the horizontal line test, but we did something to make it possible? Parabolas, right? Do you guys remember good old parabolas? So here's a good one. Here's a parabola. Right? Sure, I think it's funny. I'm sorry. Here's a parabola. That doesn't pass the horizontal line test. What did we do so that we could progress? What did we do so that we could actually find an inverse? Does anyone remember? Cut it in half, basically. We restricted the domain, right? We did this a couple times this semester. Restricted. I really want this thing. This is almost too silly to believe. This doesn't pass a horizontal line test because a horizontal line goes through more than once in at least one place. So what do? You just erase this side. Now, in some sense, that feels a little bit like cheating. Do you guys agree with me? Like, how do you just erase part of it? Well, if I want to find an inverse, I must not allow part of it to show up. I can't. So this is the only way to make something that makes sense as an inverse. And in fact, this makes sense because what does the square root function look like? In the air, do it for me. What's the square root function look like? Anybody? No? Okay, there it is, sort of. Okay. This. If you go like this, isn't that part of a parabola? It's missing this side. Oh yeah, it's missing this side. Of course it is. Because if I kept that side, it wouldn't be a function anymore, would it? And again, that's why the horizontal line test is the way it is. If I flip it and then do the vertical line test, okay, just don't flip it and do this horizontal line test instead to see if an inverse function exists. So we have done this before, what we're about to do. We have restricted the domain. Maybe. So, does anyone have a suggestion on how to restrict this guy's domain so that it's actually invertible, so that it passes the horizontal line test? So you can see the problem, like right here, this hump. That's a problem, correct? There's no hump, that's a problem, because it definitely doesn't pass the horizontal line test. So if I draw a horizontal line, it goes through more than once. So what's the quickest way to make that not happen?
Restrict it to not go past negative pi over 2.
And?
Pi over 2.
Yes, so if I cut this part off forever, and if I cut this part off, and again, I'm not given a problem and I'm changing the problem. I am just saying, could there be an inverse function for sine? Yes, if you restrict the domain. So let's look at this by itself. Very good. Alright, so now I've got negative pi over 2, pi over 2. If I let it go a little bit past here, oh shit, it kind of curves back on itself. If I let it go a little bit past here, oh shit, it curves back on itself. So I have to chop it right there. So the domain, to have sine, for this to have an inverse, I must restrict the domain to negative pi over 2 to pi over 2. Okay. Just like we did with Pres. And we did that a couple times. Okay. So this has got implications for later. And you'll see that pretty quickly. What's the range, of course, of this? What's the range? Negative 1 to 1. Just like sine and cosine always are. Okay, you guys semi with me as I get some hiccups? Oh, yeah, that's better. All right. Now, let's do like we did when we developed logarithms. Let's just graph what the answer looks like. We could do that immediately. Can somebody remind me, how do I graph the inverse given this? Say again? What's a point that this goes through? Let's collect some points that this goes through. 0, 0, I love it. So it goes through the point 0, 0. Goes through negative pi over 2, negative 1, and it goes through pi over 2, 1. I like it. Right? This is one of the best things in the world. It has to be. How do I graph the inverse? What do I do? Let me not put it there. Let me put it over here. Let me use a better pen. Sure. No, you're not a better pen. Ah, here we go. Inverse sine. This is the symbol for inverse sine, by the way. In fact, remember F inverse looks like that? So we just use the same idea. We just put a little negative 1 there. It means the inverse sine. It doesn't mean 1 over sine. Right? What's 1 over sine x? Cosecant x. Right? So that's not what this means. This means the inverse. So can somebody tell me a point that's on the inverse? Say again? A point, right? What's one point that's on the inverse? Negative 1. Negative pi over 2. 0, 0. I'll do that one. And then the last one? 1 pi over 2, right? Isn't that the greatest thing about freaking inverses? Graphically, algebraically, what do you do to find the inverse? Switch the x and y. That's too freaking awesome. You gotta love that. It's one idea that applies to multiple things. So see, what does this look like? So I need negative 1. What's negative pi divided? What's pi divided by 2? So what is pi roughly? What's pi roughly? 3.14, right? Roughly. It's not equal to 3.14. So what's pi divided by 2? 1.57. I like it. Good try. I'm with you. So this is roughly 1.57, negative 1.57. So where's negative 1? About right there. So if I want to graph the point, negative 1, negative pi over 2, here it is. 0, 0. And then 1 pi over 2. So it's going to look like this. Oops, Jeff. Funkadelic. It looks a little bit like a cube. Right? Now, to be really honest, I don't care too much about the graph of the inverse, but we might as well do it once just to kind of have it up there, right? Guys, so, remind me, how do you find inverses? Any situation, how do you find inverses? Switch the x and y. What is domain again? What does domain mean? It's a collection of all what's? X values, and what's the range? Collection of all the y values. So, what is the domain of the inverse sign? If you switch the x and y, what's the domain of the inverse sign? Negative 1 to 1. What's the range? Okay, maybe. So what this means, okay, let's do this immediately. I know we've only done one trig function, one inverse trig. We'll do the other ones. I want to focus on this right now to really show you immediately the implications of what we just did. Okay. Let me see. Keep this up here. So tell me this. This is going to seem a little funky. If I'm given a function, in fact, let's do this. I'll give it away. Really give it away. What is the input? Physically, what is it? Like, what word would describe what I'm putting in there? It has to be what? Can it be a side length? Can it be an area? What is it that I'm putting in there? Okay, maybe, or it could be a degree, but what is it then? What does that measure? The size of an angle. Does everybody agree? What do you take the sine or cosine of? Don't you take the sine and cosine and all that stuff of an angle? Yes? So, for sine, the input is an angle. And the output is just a number. So for inverse sine, and again, this is so beautiful about inverses. Everything that's x becomes y, everything that's y becomes x. What is the input now? Say again? A number. And what's the output going to be? Angle. Right? Is that cool? X and y is just switch. So if you take the sine of an angle and get a number result, you'll take the inverse sine of a number to get an angle result. So, you guys help me out. Remind me, what is sine of pi over 6? 1/2. Pi over 6 is closer to x. Sine doesn't like it. It's going to be small. It's going to be 1/2. So what is the inverse sine of 1/2? Pi over 6. So just like with any inverse function we've ever done, you must think backwards. Right? So real quick. Oh shit. What's the log base 3 of 27? 3. Why? What did you actually think about? Say again? I'm sorry? Oh, yeah. So you had to think backwards. What power would I raise 3 to make 27? You didn't actually do something to 27 necessarily. You thought backwards. So when I give you an inverse trig question, your thought process is, what angle gives me this? Right? What angle gives me a sine of 1/2? And that's pi over 6. Because sine of pi over 6 is 1/2. Right? So So you got to think backwards, which means the worse you are right now, knowing the trig angles and their values, you're definitely not going to be able to do inverses, right? You have to know what cosine of pi over 3 is to be able to do inverse cosine of 1/2, right? If you don't know the first, you can't think backwards. So, even though we haven't really discussed it yet, we got to discuss it immediately, but let me just kind of throw this at you. What is the inverse cosine of negative 1/2? Oh, Jeff, that's evil. Oh, well, too bad. Not quite. That doesn't give you negative 1/2, does it? So what would give me negative 1/2 would be back here. What reference angle do I want? Pi over 3. So what's the actual angle? You can do it. 2 pi over 3. Right? From pi over 3, if I'm 1/3 of a pi away from a full pi, I got 2/3 of a pi. Right? So this is equal to 2 pi over 3. And maybe, let's do sine. What's inverse sine of 0? What are you thinking to yourself? You're thinking the sine of what is 0? 0. What's inverse sine? Now here let's see if you guys have been paying attention. Of negative 1. What's the range of inverse sine? Negative pi over 2 to pi over 2. Right? Sine of pi over 2 is positive 1. So what's the inverse sine of negative 1? See? Pi over 2, sine of pi over 2 is positive 1. Negative pi over 2. Isn't negative pi over 2 give you a negative 1 sine? Right? Okay. Maybe. You guys start to understand, it's a lot like logarithms. If you don't know what power to raise 2 to get 8, you can't do log base 2 of 8. You can't. There's no way in hell you're going to do it. Because that's what you think. What power do I raise 2 to get 8? That's what you think. Same thing here. What angle do I take the sine of to get negative 1? Negative pi over 2. Why can't I say 3 pi over 2 here? Isn't sine of 3 pi over 2, isn't that negative 1? Why can't I say that? Why wouldn't inverse sine give that to me? Because its range is restricted. Because we had to restrict the domain in the first place. It's not its fault. Poor little dude. Maybe you guys get this. Okay. That's going to create some issues later. We'll see that once we get some more examples down. So, let's look at cosine. No good, no good, no good. Okay. So f of x, cosine x. Very quickly, if I graph this, let's graph it on the same kind of thing. We'll see very quickly what's going on here. So let's kind of do this together real quick. What's cosine of 0? 1. I love it. It loves it on the x-axis. 0 degrees on the x-axis, it's at 1. What's cosine of any kind of pi over 2? That's 90 degrees. What's cosine going to do there? 0. And what's cosine of pi or negative pi? Right, either way, I end up at the same place. Yes, what's cosine of 180 degrees? Negative 1. Right, so here's what cosine looks like in this interval. And it goes forever, of course. So again, we have the same issue. We have the exact same issue. The way it is now, no inverse can exist because it doesn't pass the HOLT, the horizontal line test. Yes? Do I want to use the same domain we used for sine? Will that work? No, no, that sucks. So does anyone have a suggestion on where to start and where to stop so this passes the horizontal line test? Do you see how back here is a complete reflection of this one? So does it make sense to sort of erase this part and only do this part? So if we restrict our domain to only be between those, this to this, oh crap and a half, Jeff. So if I restrict my domain to be from 0 to pi, then it's invertible. Do you guys see that? It's got to pass the horizontal line test. It has to. So can I do something to make it pass that test? Yes, I can restrict the domain. Maybe. And what's the range then? Of course, the range is still -1 to 1. So then if I go to graph the inverse, I want to graph inverse cosine. We'll have this working. You work, I think. Yeah. So here, what points does this go through? It goes through 0, 1, pi over 2, 0, and pi, -1. So what points will my inverse go through? 1, 0, 0 pi over 2, -1 pi. So let's see. 1, 0, so 1 is about right here, remember, because that was 1.57. So 1, 0, 0 pi over 2, so pi over 2 is a little bit above 1, and -1 pi. Let's see, yeah, -1's roughly there. It doesn't matter, John. -1 pi. Where's pi? Pi is way up here. Jiminy Crimson, sorry. Way up there. Okay. So it's going to look like, oh, the macarones. Yeah, -1 pi. Okay. Funky. And again, it's got the reflection right through the y equals x line. And again, the graph is not terribly important. We're not going to do a ton of stuff with the inverse trig graphs. I just want you to see it at least once. The important thing is inverse cosine. The outputs for inverse cosine has to be within 0 to pi. Right, because the range and domain, so what's the domain of inverse cosine? It's going to be -1 to 1, right? All the y's change to x's when you do inverses, right? You switch the x and y. So the domain and range flip. And the range is going to be 0 to pi. Maybe. So, I did not bring calculators, darn it. So let's do something together. If you have a calculator, I'll do it up here too. You're a weird little dude. Okay. Just real quick, just one little thing I want to do. So if you have a calculator, do this with me. Let's see. So let's make sure we're in radians. So mode, I'm currently in degrees. Let me change to radians just to be safe. Okay, so if you got your calculator, let's try something out real quick. Let's do sine of, let's see, Jeff. Yeah, sine of pi, let's do 2 pi divided by 3. Sine of 2 pi divided by 3. Okay, now that's one that we should be able to tell. That's rad 3 divided by 2, right? Just to kind of verify. Is everybody cool with that? Isn't this sine of 60? So it's rad 3 divided by 2. Do you see how those are the same number? Of course they are, because that's what that is, right? But now let's do you guys see your inverse signs, right? This is beautiful. Sine, inverse sign, right above it. So let's do inverse sine of rad 3 over 2. Now we just did sine of 2 pi over 3, and that was rad 3 over 2, correct? You guys with me? So the inverse sign should kind of undo what we just did, but what do you do? What do you get? Well, it's going to be a little weird. When you do this, you get this, which is not 2 pi over 3. That's actually pi divided by 3. Do you see that? That's pi divided by 3. Okay. I should have picked. Yeah, that's true. I should have picked that. Let's try it. Let's do one more real quick. Let's do a better one. Sorry. I want something with a little less decimals in it. So if I do sine of, you can do it, Jeff. Yeah. 5 pi divided by 6. Not surprisingly, I get a half. Because 5 pi over 6, the reference angle is pi over 6, is 30 degrees. Sine doesn't like it there, 1/2. But if I do inverse sine of a half, do I get 5 pi over 6 back? No. I get pi divided by 6. This might be, let me do one thing. Let's change to degrees. I really want you to be able to see this without all the decimals in the way. So let's try this again. If I do sine of 120, what's the reference angle? How far from 180 is that? 60. Okay, so again, this should be, let's not do that then. Let's do 150. There we go. Make sure you're in degrees, right? So if I do sine of 150, the reference angle is 30 degrees. This should come out to be a half. And did I change the degrees? Yes. Okay. So we get a half. If I do inverse sine of a half, do I get 150 back? No, of course I don't, right? Because who remembers? What's the range of inverse sine? Negative pi over 2 to pi over 2. Because that's all it can give me. Because the way what we had to do to even make it exist was to cut the domain of sine to negative pi over 2 to pi over 2. It's not this poor little dude's fault. It can only give us reference angles. It can only give us from negative pi over 2 to pi over 2. That's all it can do. So when I get 30 degrees, that might not be the answer. If I'm in quadrant 2, that can't be the answer. The answer must be 150. So because of how we had to cut the domain of sine, inverse sine can only give us some angles. It can't give us every possible angle. We have to know when that means 150, if that means 210 degrees. What is the sine of 210? You shouldn't need a calculator to do it, right? The reference angle is still 30, but now it's down, right? So what's the sine of 210? It'll be negative 1/2. Bam. But if I do inverse sine of negative 1/2, I do not get 210. I can't. The poor little dude, we restricted it. It's going to do the best it can. It's going to say negative 30. So we have to understand that is a reference angle. Maybe. Yes. Because again, the only things sine is allowed to give me, of course this is from earlier, is from negative pi over 2 to pi over 2, yes? That's why we wrote down the range of inverse sine is negative pi over 2, negative 90 degrees to 90 degrees. So what if the answer is supposed to be 120 degrees? Can it give that to me? No. It is stuck between negative pi over 2 and pi over 2. It is stuck between those. So the best it could do is give me the reference angle. That's all it could do. In fact, when we're doing sine of 210 degrees, what's the very first thing we do? We find the reference angle. Yes, maybe? So of course the inverse sine is going to kind of undo that. It says, okay, here's that reference angle you would have found. You have to know what quadrant you're in, human. You made me. I don't know shit. Right? So we have to understand what it's trying to tell us. It couldn't exist unless we restricted things. Poor little dude. Okay, maybe.
In doing the reference angle, do we do it closest to the quadrant?
Oh, yeah. Say again?
When
Oh, okay. Let's try an example. Okay. Let's do an example. Let's do a nice concrete example. In cosine, of course, inverse cosine is going to give me between 0 and pi. So let's do a couple examples. So let me just write that down just to remind us. So inverse sine, the range, negative pi over 2 to pi over 2. Inverse cosine, the range, 0 to pi. So let's say I have theta is in quadrant 3, and I know cosine theta equals, 1/2, negative 1/2. What is theta? Well, if I do the inverse, let's see if this makes sense for you guys. I should be able to figure this out without the calculator itself. Well, let's do this. If I do inverse cosine of both sides, so you guys see how this works? It's exactly the same way we solve any equation. We apply the inverse function. So I have to do the other side, inverse cosine of negative 1/2. What do these do to each other? Cancel. So the angle is inverse cosine of negative 1/2. Do that in the calculator. What does it tell you? Well, stay in degrees. Let's work in degrees for the moment so we don't get some funky decimals. So try to do inverse cosine of negative 1/2. What do you get? Oh shit. Oh, duh, Jeff. I used the minus symbol instead of the negative symbol. Yeah, so I get 120. Is that the right angle? What quadrant am I supposed to be in? Is that in quadrant 3? So it gave me 120 degrees. It has a reference angle of what? 60. So my actual answer should be 180 plus 60, 240. So again, the inverse trig functions, this is not really a reference angle because it lives between 0 and pi. So I just have to understand, if this is negative, it's going to give me something here. And if I'm supposed to be here, I got to figure out what that actually is. If it's positive, it's going to give me something here because it can only live between 0 and pi. And if I'm supposed to be in quadrant 4, I have to do the same thing. I have to figure out where am I actually at. And again, why does it do that? Because it wouldn't exist otherwise. It couldn't exist otherwise. Maybe. So it's going to do the best it can. Okay. So, before we do tangent and all that kind of stuff, let's just focus on sine and cosine for a minute. I want to show you what this does for us. So if I have this triangle, and I know this is 7, I know this is 11. I want to know what the angle is. What can I set up? What trig function
Sine.
relates what I know? I love it. So what's sine theta? How do I solve for theta?
Reverse sine.
Yes, I apply. That's good, Jeff. You drop the, I'm going to pick up a ball. I have to apply the inverse sine to both sides. I am not multiplying both sides by inverse sine. That doesn't make any sense, right? If I take the square root of both sides, I'm not multiplying by the square root symbol, correct? So it doesn't make any sense to put inverse sine back here. Don't do this. That makes 0 sense. That's like saying x squared equals 9, so then square root, x equals 9 square root. No. Right, you've got to take the inverse function of each side. So what does this do? Dies. I love it. So theta equals, and what do you get when you plug that in? Anybody? What do you get when you plug in? Is everybody still in degrees? Hopefully?
It's like 39.52.
Oops. Yeah, 39.52 roughly. So I tell you how many decimals to round to, yeah. You guys see that? Roughly? All right, let's try something real quick. So you see the immediate power of this. I can calculate angles just by knowing the sides now. That's something we were never able to do. Now I can do it. We can figure out what the angle is. Let's see. Can somebody tell me what this side is? What would you do to figure out this side?
Pythagorean theorem.
Pythagorean theorem, good. Okay, so I'm going to do it 2 ways. First way, I'm going to do P theorem. What's that say? How do I figure this out? Let's call this B. What did I set up?
7 squared plus b squared equals 11 squared.
Good. So B squared equals 121 minus 49. So B squared equals 72, I believe. You guys semi with me? Yes, yes. So B equals the square root of 72, which is 6 rad 2, which is roughly 8.4 maybe?
It's 8.48, so would you round up?
3.48, blah, blah, blah?
Yeah.
Okay. You guys all with me? Is that okay? That's old news. Ooh, Jeff, Pythagorean theorem. Ground shaking, right? Let's figure out what that side is a different way. Does anyone have a different way I can figure out what that side is? Do we know what that angle is now? It's this, right? So how would I figure out what that side is? Using this angle. Well, what trig function would relate anything I know? What would you could, there's a couple of things you could choose. Yeah, so we use cosine. So here, what would cosine of 39.52 degrees, what would it be? B over 11. Now I better get close to this, or this whole thing is shit. And so Jeff is up here going, oh man, did I write everything down right? We're going to find out. How do I solve for B? Multiply by 11. So what's 11 times cosine of that? Maybe. Of course it is. It's the same side. So Pythagorean theorem works, trig functions work. They have to agree because they're both valid. So that's not an amazing thing. You might not have gotten the exact same answer because I rounded this, right? This is rounded, so it's going to be a little off because of that. So let's look at tangent and cotangent really quick. They're going to be much, much easier. Can you very quickly graph the tangent function for me? One cycle. I'll be really nice and say do it between those. What happens at these positions for tangent? Asymptotes. And what's it basically look like in here?
Cubic.
It looks like a cube, right? It looks cubish, right? We know at pi over 4 pi is supposed to go through 1 blah blah blah. That's the basic look of it. And then it continues forever, but do you see how, is this invertible? If I just don't draw any of the other infinite tangent images, is this invertible? Does it pass the horizontal line test?
Yeah.
Yes, so it's got a natural thing. I want to restrict the domain to be negative pi over 2 to pi over 2. It just has a natural thing. I don't have to do weird shit to it. I'm just like, let me just draw one instance. Ah, that's invertible by itself. And what's the range? Negative infinity to infinity, right? So, if I graph the inverse tangent, just to do this kind of quickly, inverse tangent, this goes through 0, 0 for sure. It's going to have an asymptote at pi over 2 and negative pi over 2 this way. They have to turn. And then if I think about reflecting it around this line, it's going to look like this. Jeff? Interesting. So it just sort of falls over. The major thing to recognize there is if you do the inverse tangent of something, it will only give you, right? Because what's the range of the inverse? It's going to be, what's the domain of the inverse? It's going to be the range of the original, right? They switch, x and y switch. So the range will be negative pi over 2 to pi over 2. Jeff, make these, you can't include those, but they're asymptotes. All right, Jeff. Sorry. So the same problem happens. If you do the inverse tangent and you're supposed to be in the third quadrant, it's not going to give you an angle in the third quadrant. It's going to give you a reference angle. Just because of what we had to do. We had to restrict it. Poor little dude. And then there's something, I don't think we really spent much time on this, but cotangent, very quickly. Where should the asymptotes be for cotangent? What is cotangent? What trig over what trig? Cotangent is cosine over sine, right? Where's it going to have an asymptote? Wherever sine is 0. Where's sine 0? 0. What's the next place at 0? Pi. And in the first quadrant, these are both positive, so it starts off up here, and then when you get to the second quadrant, cosine's negative, sine's positive, so now the outputs are negative. So it looks like tangent just shifted and reflected. And again, it's got the same thing. It's completely fine the way it is. If I just don't draw any other images that go forever in both directions, I'm golden. So I want to restrict the domain to be 0 to pi. And the range, of course, is negative infinity to infinity. So the inverse cotangent is going to go from 0 to pi. And it's going to go, for example, it's going to go 0 pi over 2. Let's see. 1 goes to, pi over 4 goes to 1. So 1 is going to go to pi over 4, roughly. This is going to be freakadelic. I hate it when it's like this, poor little dude. Yeah, so it's going to roughly do like this. So again, it kind of looks like the, oops, I completely missed that, make that really big. It's going to kind of look like the inverse tangent just kind of shifted a bit. And again, I'm not too concerned about the inverse trig graphs. I want you to be able to use them. So the big thing to realize here is when I do an inverse cotangent, it's only going to give me stuff between 0 and pi, the same way as inverse cosine does. Maybe. So, if I want to solve, let's see, let me keep all this. Tangent theta is negative 0.15. Right? What would you do to both sides? What would you do to both sides? Be careful how you say it. You're not multiplying. You're taking the inverse, right? You wouldn't say you solve a square by multiplying by the square root. You would take a square root. So I'm going to take the inverse tangent of both sides. Let me tell you that theta is in quadrant 4. I'll tell you that much. So what do you guys get when you do that? I think we all should still be in degrees. So the problem will tell you if it wants radians or degrees. So if I do inverse tangent of negative 0.15, I get, oh, am I in, oh yeah, that's right, I'm in radians. No, I'm in degrees, okay, good. That's right, negative 8.53 degrees. Is that angle where I'm supposed to have it? Is that angle in quadrant 4? So if I start at 0 and I go back 8.53 degrees, what quadrant am I in? Quadrant 4. I'm in the right quadrant, correct? I don't have to change anything. Maybe. So I'm basically done. I just round it to whatever place the thing wants me to round to. What if I would have the exact same problem, but I say quadrant 2? I still take the inverse tangent. These kill each other. I still get negative 8.53. But is that in the second quadrant? No. So what I want to do is, the way to look at this is actually it says you go back this many degrees from 180. So the really funny thing is, with tangent, what's tangent's period again? What's the period of tangent? Pi. So if you add pi to this, in fact, add 180 degrees, that will effectively put you where you're supposed to be, quadrant 2, yes? 180 minus 8.53, that'll be 171.47. Do you understand how the answer you get might need adjustment because of what we had to do to make the inverse exist in the first place? It can only give me so many values. We're the humans. We have to go, oh shit, I'm not in the right quadrant. I got to get there. Okay, let me see. Okay, that doesn't come till later. That's true. Okay. I don't want to do that too soon. Okay. Yeah, okay, so one last thing to do. Okay. So later this semester, which can't be that much later because there's not much of the semester left, we will solve trigonometric equations. We're not quite there yet. Right, so that is in our future. And that's going to be interesting because can anyone tell me how many answers does this have? How many answers does that have?
4?
Nope.
1?
Nope. Nope. Infinitely many. What's the first quadrant angle that gives you sine equal to 1/2? What angle does that? In the first quadrant, what angle gives you sine equal to 1/2? 30 degrees. What else is 30 degrees? Can't you go around? Isn't 390 degrees also in the same place? Well, for you guys, this, right? Can't I do that forever? Can't I go backwards forever? So technically, that has an infinite number of answers. So we're actually going to give all the answers to that when we do it. Thankfully, it's not going to be a list. It's going to be a little statement, right? So we'll get there. So that's in our future. Just wanted to lay that for right now. Okay. So one last thing in this section. One last thing. So let me do it this way. Yeah, let me do it this way. Do you remember one of the first things we did with trig, once we got the basic ideas down? If I told you sine theta equaled 7/8, right, now we know we can take inverse sine, we can get the angle, but before we knew inverse sine, am I able to draw something and tell what other trig functions are? Can I do that? Like if I wanted to know, if I wanted to know the tangent of theta, how could I figure that out? What can I draw based on this? What kind of triangle? Right triangle, holy shit. And then what do I know? If I put the angle right there, what side is 7? The y side. And what side is 8? Hypotenuse. That's right. Do you guys remember this? This was just right off the basic definition of sine. Sine theta is the ratio of the y side to the hypotenuse. So if I know it's 7 to 8, I know it's 7, 8. And then you could tell me, how do I figure out what the tangent is? I could just do Pythagorean theorem, right? That's not what I want to do right now. Okay. This whole problem is now going to be given to me in a different way. So let me ask you this. Okay, let's build this. Let's build what we're going to see. So if I see this, how would I solve for the angle? Inverse sine, 11. So it would be theta equals inverse sine. I really want you to understand what's happening. When you see this, can't you draw this triangle? Isn't this and this, aren't they equivalent? Aren't they saying the same thing? Do you guys agree? Aren't they the same equation? I just solved it a little bit, yes? So if I see this, I can draw this triangle same way. Now what am I actually asking for? Tangent of theta. Well, what's theta? Isn't theta this? So the question would actually look like this. What's the tangent of the inverse sine of 7/8? That is what the question is going to look like. And how do I do it? Well, I say, okay, this tells me a triangle that looks like this. How do I get the tangent? I just need to get the x piece, right? How do I get the x piece? A little 8. Pythagorean theorem. 64 minus 49, right? 15. So square root of 15.
Does the inverse of sine, does that change the y and hypotenuse?
No. No. This statement defines an angle where the sine is 7 to 8. So whenever I see inverse trig of a ratio, I can immediately draw a triangle. Now there are some situations where they're going to tell you the angle is in some certain quadrant. The same way, haven't I given you problems that said cosine theta equals 2/3 and you are in the 4th quadrant or something? So you had to be careful about the sign of the answers and whatever. So the same thing's going to happen here. So what is the tangent? What is this? What's the tangent of the angle that this creates? What's the tangent? 7 over rad 15, so 7 rad 15 over 15. Okay, so let's do a full problem straight up. So the problem from the beginning would look like this. It would say, what's the cosecant of the inverse tangent of 3/7? That's the problem. That's exactly the way it's given to you. What does inverse trig tell you again? What do you take the trig function of? What do you put into a trig function? An angle. So what does an inverse trig function mean? What's the output of an inverse trig function? Angle. So this tells you the angle. Can you draw a triangle based on that angle? I'm going to call it theta for right now. What's the triangle look like? What side is what? Say again? Yeah, tangent of the angle is 3/7, so the y side is 3. The x side is 7, right? Tangent's y over x. And what does it want me to figure out? It wants me to figure out cosecant. Now again, there's nothing wrong with saying to yourself, okay, cosecant is the flip of sine. Sine is y over hypotenuse. So cosecant is hypotenuse divided by y. Right? So I need the hypotenuse divided by y. And again, Pythagorean theorem, right? 9 and 49, square root of that is 58. Right? 3 squared plus 7 squared, 9 plus 49. And then the cosecant is hypotenuse divided by 3. Hypotenuse divided by y, because it's 1/sine. Maybe. Possibly. What if I would have told you this is in the 3rd quadrant? What if I put that on top of this? This is in the 3rd quadrant. What would have changed? Anything? There's only one thing that changes. Right? What is cosecant in the 3rd quadrant? Which is basically asking you, what is sine in the 3rd quadrant? Is it positive or negative? Negative. So this would have been negative. That's the only thing that would have changed. Everything else would stay the same. So if they tell me I'm in a certain quadrant, I can take care of that at the end. Like just make sure I put the right sign on things. Why does it make sense that tangent is positive, 3/7? Because in the third quadrant, sine and cosine are both negative. When I divide them, the negatives cancel. So that makes sense. That's why I had to stop and think for a second, which quadrants make sense here? Maybe. So real quick, here's a nifty one. What is the cotangent of the inverse sine of x over x plus 1? Don't freak out. Can you draw the triangle? Can you label the sides correctly? This is not a big deal. There's fewer numbers in here. Oh well, too bad. The process doesn't care. We care. We're the humans. We'd like some numbers. Too bad for us. But the process is the same. What's true about this triangle? It's a right triangle, sure. The angle has a sine that gives me this. So where does the x go? On the y side. And where's the x plus 1? Hypotenuse, because sine is the y side to the hypotenuse. It wants me to know the cotangent of that. What am I missing to figure out the cotangent? The x piece. How do I get that? Pythagorean theorem, but it's going to be a little grosser. Too bad. Figure out what it is. I want you to figure out what that side is. Go. Process doesn't change. The shit you plug in changes. Process doesn't change. So you guys don't trust me. Let's see. What does the Pythagorean theorem say? Yeah. So x squared plus b squared equals x plus 1 squared. And we have to solve for b, right? Keep going. Whether it's positive or negative would depend on which quadrant I'm in, and actually x itself could be negative, which could be a problem, right? But we're not worried about that at the moment. So now do I have everything I need to answer the question it's asking about this angle? What is the cotangent of the angle? What's cotangent in general? X over y. So what's the cotangent? X side, so y side. There you go. Okay. So last thing for today. Don't get too excited. It's going to take a little while. start developing. So the thing to remember is that trig functions themselves are just ratios of sides of a right triangle. I know I've said that a lot because it's important to remember that's what trig was built on. The amount of things we can do with it, given that it's just ratios of sides of triangles, is insane. We are about to start looking at that. We're about to start developing what's called identities, right? Not your own identity. Hopefully you've done that already, right? I'm not here to help you with that, but we're going to develop trigonometric identities. So statements that are true. So the very first one I want to look at. So if I'm given, let's do it this way. I'm given a triangle. Let's say that's x, that's Jeff. Let's say that's x, that's y, and that's h. What is sine of theta, of course? Y over h. And what's cosine? X over h. Crazy sauce, right? One more thing. What is x squared plus y squared?
1.
C squared, or H squared.
H squared. Okay, good. Everybody with me? So this is true for any right triangle, right? Does that make sense? This is just every right triangle. I just didn't tell you what the sides are, but these are all true statements for any right triangle anywhere in the whole universe. Okay, so what is sine squared? Nothing major. What's sine squared? And this is how we write it, by the way, right? Do you guys see that? So this means the same thing as this. It's just quicker to write. I don't have to put parentheses. So you're going to see me write this a lot. What is sine squared? Nothing major. What's sine squared? Y squared over h squared. Right? Nothing major. What's cosine squared? Everybody with me? All these things are true, correct? I mean, that's how we define sine and cosine. That's how we made them. So you can't argue with that. That's how they're defined. And then, of course, if I square them, it's amazing. I square the top of this crazy. So what is sine squared plus cosine squared? I get y squared over h squared plus x squared over h squared. Does that have like denominators? Yes? So a x squared plus y squared over h squared. Yes? Right? Is that cool? They have like denominators, both h squared. I can add the tops. But what is x squared plus y squared? What's x squared plus y squared? Freaking h squared. So see, x squared plus y squared is h squared. What is h squared divided by h squared? Freaking 1. When is that true? Always. Because I just drew every possible right triangle that ever existed and ever will exist. So that is always true. Period. What is always true, Jeff? This thing. This is crazy important. I don't know if you guys kind of follow. This is stupid important. This is crazy. Sine squared of an angle plus cosine squared of the same angle is always 1. Always, always. And if you think about it, of course it is. Another way I could have done this is, isn't everything based on the unit circle where the radius is 1? Isn't sine the y piece and cosine the x piece? So of course sine squared plus cosine squared equals 1 squared. Sine squared plus cosine squared is 1. But I wanted to show you it works for any triangle anywhere. It doesn't have to be unit circle, right? So what, Jeff? I don't know. So help me out. Let's try this on a few things we know. What is sine of 30 degrees? One half. And what's cosine of 30 degrees? So what must 1/2 squared plus rad 3 over 2 squared? It better equal 1, correct? Sine squared plus cosine squared is supposed to be 1. That's what the thing said. Well, what's 1/2 squared? Crazy sauce. And what's square root of 3 squared? 3 and 2 squared, 4. 1/4 plus 3/4? 1. Crazy. That works for everything. What about at 45 degrees. They're both rad 2 over 2, right? Rad 2 squared is 2, 2 squared is 4. Rad 2 squared is 2, 2 squared is 4, 2 fourths plus 2 fourths is 1. Crazy shit. Fundamentally, this is because sine is y, cosine is x, and they come from the unit circle. So of course sine squared plus cosine squared is 1. Of course it is. Maybe. So, I keep doing this, I know, but. Let me think. Oh, okay. If I start with this, that is a fact. I don't know if I can impress upon you enough how important that is. That is the most fundamental identity for trig functions. I'm going to give you eventually the sheet of paper. It's all kind of got green stuff on it. It's got all the trig laws we're ever going to learn. There's going to be a line. Everything above the line you have to memorize. This is definitely one of them. Everything below the black line, you're not going to have to memorize. Right? So anything I don't personally have memorized, I'm not going to make you memorize. Only kind of makes sense. It's better than old gym teachers who were not able to do one push-up, and they're making us do push-ups. So anything I don't have memorized, you don't have to memorize. Now, let's just mess with this. Let's mess with this. Can you take a second and divide both sides by cosine squared? I'm going to do it like this. Divide by cosine squared, divide by cosine squared, divide by cosine squared. What do you get? What's sine squared divided by cosine squared? Tangent squared, right? Sine over cosine is tangent, so sine squared divided by cosine squared is tangent squared. What's cosine squared divided by cosine squared? 1. And what's 1 over cosine? Secant, so 1 over cosine squared is secant squared. There's the second level identity. These are, not surprisingly, these are called the Pythagorean identities. Didn't we build this first one on the Pythagorean theorem? So these are called the Pythagorean identities. So here's the second one. You must memorize this. Or you could just memorize this one and then divide by cosine squared to get what you need. That's what I do. I have a lot fewer laws memorized. I make the ones I need when I need them. You don't have to do that. You can just memorize all of them. Do the exact same thing, but what do you think I want you to divide by now? Sine squared. So go ahead, take a second. Divide everything by sine squared. Look something up real quick. Let's see. No, that's not what I want. No, that's not what I want. All right, what do you guys see? Sorry, I was trying to find this animation here. So if I start with sine squared plus cosine squared divide by sine squared, I get 1 plus cotangent squared equals cosecant squared. I want you to see the analogy here. Watch this, watch this. What's 1 plus tangent squared? Secant squared. What's 1 plus cotangent squared? Cosecant. Holy shit. Right? We're starting to see reasons we called the co-shit co and the not co-shit. We didn't give it a co. We're starting to see why. When we first did it, it didn't immediately make sense. Why would secant go to cosine and cosecant go to sine? What the hell? Why is that a co? We're starting to see why. Because the co stuff seemed to go together. The co stuff seemed to share some things. And the non-co stuff, same way. Maybe? I'm trying to give you a way to memorize this if you want to. Okay, maybe. So. How would this show up in a problem? Let me get one right out of the book. Alright, here we go. No, get away. Go on. Oh yeah, where's that good one? No. Okay. Yeah. No. Yeah, let's do that. Okay. All right. So we got these facts. We know these things. So there's 3 identities we have so far. So if I wanted to show this is true, cosine theta over 1 plus sine theta, I want to verify that this is a true statement. Is it 1 minus sine? Yeah, over cosine. All right. Some of you guys see that. You're going to turn off a little bit. This is not immediately obvious. It is not. In fact, it sort of doesn't make sense, right? How could cosine divided by 1 plus sine equal 1 minus sine divided by cosine? What the shit? What's going on? Okay. Today is kind of a huge day. Right. So we got our identities. We got the most fundamental identity. Sine squared plus cosine squared equals 1. This is a really big moment for you in mathematics. This is where, in pre-calculus, you do a lot more of this than other classes that you've taken before. You're going to continue to do what I'm about to say forever. You're going to play with stuff. You're going to play around. You're going to try stuff and it's not going to work and you're not going to care because that's part of the process. What's part of life? You try to solve something, it doesn't work. You just lay down and go, this is my life. No, you try something else, don't you? You go, well, that didn't work. Okay, let me try something else. So that's what these entail. Guessing something to do and having it go nowhere is possibly part of the process. Are you listening to me? That doesn't mean you don't know shit, right? If somebody just gave me a trig function, a trig identity, I might make the wrong, let me try this. Well, that didn't work. It's not a big deal. It doesn't mean I don't know math. It doesn't mean I suck. It doesn't mean anything like that. It just means that's part of the process. That's what I mean by play. Right now, this is really brand new to us. We just learned these identities and such. This is a little bit, I like this one. It's not immediately obvious. There's so many cool things to this, though. All right. The way you do this, we're trying to prove this is true, correct? We're trying to prove this equality is true. How do you normally solve an equation? So this is kind of silly, but how would I solve this equation? What would I do? What would you do? Okay. That's all right. So you subtract 1 from both sides, right? Why am I allowed to do that? Does anyone know why I'm allowed to do something like that to both sides? Say again? No, it's not why I'm allowed to do it. That's what I want to do. I'm allowed to do it because the equality is given. We know it's true. This question says, show that this equals that. if you're verifying identities, you cannot do something to both sides. Because then you're assuming the equality is true. And sometimes you doing that will cause you to go the wrong way. It'll make it look like it works when it doesn't. Okay, so what should I do here? So the way you look at this is you want to start with one side and make it look like the other side. That's the idea. You guys with me? So there's several ways to go about this. One thing you can do is you can make everything sine and cosine. Like if you had tangent and cotangent and cosine, you make everything sine and cosine. Well, it's already everything sine and cosine. That's not going to help me out. Do you see any squares on trig functions? Because aren't all the identities basically involving squared trig? All the ones we know so far, right? Nothing squared, damn it, Jeff. So I want you to see two things. Do you guys remember how to simplify this? Somehow this relates to this problem. Anybody remember how to simplify this? Multiply by the the conjugate. Multiply by the conjugate, which was square root of 3 plus square root of 4, right? Square root of 4, of course, is 2, I know. Sorry, I picked a bad number. So look here. Let's look at this side. And I want you to see why. There's two reasons why I'm going to do this. So I'm going to start with this side. What am I going to do? I'm going to do something very much, and I want you to see, you're going to see why this works here. What is the conjugate of 1 plus sine theta?
1 minus sine theta.
So if I multiply top and bottom by 1 minus sine theta, does anyone see why this makes sense to do in a different way? What is on the top of this side? 1 minus sine is on the top, isn't it? So if I multiply the top by 1 minus sine, I'm one step closer to making it look like this. So the whole point of verify identity problems is to start with one side and make it look like the other side. Now you could actually work with both sides and you're hoping that they're going to meet somewhere in the middle. You've got to have a chain going from one side to the other side, right? Let's see what this does for me. So there's two reasons I'm doing this. One is because it's there. So I'm going to multiply the top by this so that it's there. I'm one step closer to making it look like that. But another reason is the conjugate. And sure enough, what do I get on the bottom? 1 plus sine minus sine, the middle terms cancel. Minus sine squared. And on the top, I just get cosine theta times 1 minus sine theta. I'm not going to multiply it through because I know I want that there. What's sine squared plus cosine squared? Sine squared theta plus cosine squared theta is 1. So what is 1 minus sine squared? Cosine squared. You guys see that? If sine squared plus cosine squared is 1, 1 minus sine squared is cosine squared. Is that cool? So I can replace that with this is cosine squared. Now what happens immediately? Anybody see something that happens immediately? Don't I have 1 cosine up top and 2 on the bottom? Right? So I can kill 1 cosine. Yes? 1 cosine cancels. Yes? The same way, what do you do with this? If I gave you this, what would you do? What would you do? X over x squared. What would you do? How many x's are left? 1 on the bottom, right? Because 1 cancels, 1x cancels. Same thing here. How many cosines cancel? 1 of them. How many are left? 1 on the bottom. So this is 1 minus sine theta over cosine theta. Is that what we're trying to show?
Yeah.
See that I started here and I made it look like that. Done. I verified the identity. This does equal this. Yay. All right. Maybe. By the way, we're going to be doing this kind of thing a lot. And guess what? We've only learned 3 identities so far. right? There are dozens of identities. A lot of which I'm not going to make you memorize, so don't freak out. There are certain ones we're going to have to memorize, and I will tell you very specifically which ones those are. You guys with me? So we're going to develop the identities, and the minute we develop more and more identities, the more and more problems like this I can give you to verify. Yay, Chad. Some people see this as a game. I've noticed most students really don't like this, and I think it's because, again, that's why I try to make this a big point. Do not get down on yourself if you try something and it doesn't work. Big deal. Go back, try something else, right? Not a big deal. Okay, maybe. Let me say one last thing about identities here, and then we'll head out. Let's see. Does anyone remember what this tells me about a function? Or what this tells me about a function? Anybody? Does that look familiar to anybody? A parabola. What's 3 squared? And what's negative 3 squared? So f of negative 3 is the same thing as f of 3, correct? What kind of symmetry does this have? Even. Yes, y-axis symmetry, which is also called even. How do I remember that? Well, parabola is the most basic even symmetry, and what power does it have? Squared, in even power, correct? What does this? Well, what's 2 cubed? 8. What's negative 2 cubed? Negative 8. So isn't f of negative 2 equal to negative f of 2? So this would be symmetry through the origin. This is cubed, so that must be odd symmetry. And this is even symmetry. So which trig functions have which symmetries? Well, if I look at sine, what does sine look like? Doesn't sine look like this? Oh, crap in the hat, Jeff. What's even better than that if you can draw better than me? What does it look like? I love you guys. Even is symmetry with the y-axis. Does this look the same on either side of the y-axis? Doesn't it look a lot more like a cubic right through here? Yes. So sine has the property where this is true. Cosine looks like this, and that looks more like a parabola. It looks symmetric with respect to the y-axis, so cosine is got even symmetry. So that means that cosine of negative x equals cosine of x. And real quick, another way to see this, can somebody tell me what is the cosine of 30 degrees? Rad 3 over 2. What's the cosine of negative 30 degrees? Why isn't it negative? Because cosine likes x, and x is still positive there, correct? So that tells me cosine of negative x is the same as cosine of x. If I look at sine, what's sine of 30 degrees? 1/2. Well, what's sine of negative 30 degrees? Negative, because now the y piece is negative. And that tells me that sine of negative angle equals negative sine angle. Okay, maybe. That's the even and odd symmetry of those. Okay, so all that can come up, and that's homework. I think that's plenty for today. Yes. So let me know if you have any questions left over about the test or your grades or anything.